Hi, I'm Ali from University of Warwick. Currently, we work on using machine learning to improve data systems under supervision of Professor Trantifilio. And with this presentation, I'm going to explain how we solve random joint sampling problem by using graphical models. Assume we have two tables, T1 and T2, with a shared attribute C. If we join these two tables and find the join result, and if we give the same probability per tuple in the join result and make a sample based on those probabilities, it will give us a random or uniform sample of the join result. But sometimes these tables are too big, and joining the big tables will take a lot of time, maybe days or weeks. And also sometimes the join result is very huge, and storing and analyzing that huge data will be expensive, especially if we do all these things in the cloud. So the question is how we can generate this uniform sample without generating the join result. In fact, we want to generate these uniform samples directly from the tables. So there are some related folks. For example, we can sample the tables and join the samples, but this is a well-known problem that it will not generate a uniform sample of the join result. Alkin and Chowdhury, in different papers, they introduced some algorithms to generate uniform and independent samples of the join result. Both of them are applicable only on two-way joins. By the way, Alkin's approach is not efficient because it uses rejection sampling. Zhou, in his ICMO 2018 paper, which is the state-of-the-art method, extended those two algorithms to n-way joins. But the algorithms in Zhou's paper are complex and they are not easy to understand. And since they calculate the frequencies per tuple in the tables, they are not very efficient. In this work, we use principal probabilistic graphical models, which it has some algorithms that are easy to understand, to generate a uniform and independent sample of the join result. Since we calculate the frequency per distinct value in attributes, so our algorithms are more efficient than Zhou's algorithm. Our approach and also Zhou's approach can be applicable on chain, acyclic, and cyclic join queries. But what are PGMs? PGMs provide a global understanding based on local observations. For example, this is an MRF, which is a kind of PGM with three random variables, A, B, C, and ages between them, which shows the dependency of the variables. These dependencies can come from local observations, and PGM can provide us the joint distribution based on those local observations. And for example, in this case, we don't need to catch the relationship between B and C because we know B and C are independent from each other if A is observed. So PGMs can provide us a simpler factorized distribution that help us to have efficient algorithms. So the joint distribution can come from this equation, just multiplying the local observations in the edges. We say these PGMs are a natural map for relational data because these local observations can come from different tables. For example, the dependency between A and B can come from table 1, and the dependency between A and C can come from table 2. And if we multiply those local observations, it will give us the joint distribution of the join result. So we can make samples from that distribution. This is overview of PGMJoins. PGMJoins get a join query and makes an MRF. For any attribute, we create one node, and if those attributes are in the same table, we create an edge between those nodes. We separate non-join attributes from the join attributes. The black ones are join attributes because non-join attributes don't affect the uniformity of samples. So we generate the samples from first for join attributes, and at the end of the process, we can add non-join attributes in the sample. Once we created the graph, we start doing inference from the leaves to the root, and we calculate some statistics during this inference. And then once we reach the root, we start generating the samples from the root to the leaves. Once we generated the sample for join attributes, we simply add the samples of non-join attributes in the main sample. This is an example that shows the full process of the join sampling. So imagine we have 6 tables with some shared attributes, and this is the join query. We need to learn the structure of the PGMs, which includes qualitative and quantitative components. In learning qualitative component of the PGM, we just find the name of the nodes and the ages between the nodes. But in quantitative component, we learn the actual dependency between the variables. So if these are the tables and we create a node per join attributes, and we also create a node for all non-join attributes that are involved in the join query, because we can, for example, in this case, we can, we can add A, B at the end of the process together. So we don't need to have different nodes per A and B, because they are non-join attributes. If 2 join attributes are in the same table, we need an edge between these 2 join attributes because they are dependent. And as I said, for any non-join attributes, we need an edge from all the join attributes in the same table to that non-join attributes. And this is the final MRF from these tables. These are non-join attributes. So since the query is not cyclic, the graph also is not cyclic. So we can assume it is a tree, and any tree, we can assume each of the nodes as the root of the tree. So I just chose I for this example. Any tree has a perfect elimination order. It means that we have simple shells in the leaves, and we can eliminate the nodes one by one without adding new edges in the graph. So we can eliminate first C, then G, then K, and then I. And these are our non-join attributes. In quantitative learning, we scan the tables one by one. If there is just one join attributes in the table, we calculate unconditional frequency table that shows the frequency of each these distinct values in this table. And also we calculate a conditional frequency that gives us the frequency of all the non-join attributes, given all the join attributes in the same table. If we have 2 join attributes in the same table, we need to calculate a conditional frequency table for the join attributes. For example, in this case, since we eliminate C before G, we need the frequency of C given G. So we can, during scanning this table, we can calculate those frequencies. By the way, we scan the tables only one time. Once we calculated all the frequencies, we can eliminate the non-join attributes from here and just do inference on the skeleton of the graph, which includes all the join attributes. At the end, we use these conditional frequency table of non-join attributes to add non-join attributes in the sample. We use variable elimination algorithm for doing inference. So the trivial approach is to find the join distribution is finding all the marginals like this, the probability of I in the join distribution, probability of G given I, and probability of C given G, and probability of K given I. And once we found this, we can generate the samples. But to find these marginals, we need 2 times message passing if we use message passing algorithm. So we need to do elimination, run the elimination algorithm from the leaves to the root and from the root to the leaves. And once all the nodes get all the messages from the parents and children, we can calculate these marginals. Since it needs 2 times message passing, so it is not very efficient. In this example, I will show how we do it more efficiently. We just do one-time variable elimination from the leaves to the root, and we find the marginal for I. During eliminating these nodes, we calculate some other statistics that they help us to generate uniform samples without running the second phase of the variable elimination in message passing algorithm. So to find the marginal of I, we need to multiply all the local observations that we have in the edges and then sum out CGK, these variables, to find the marginal for I. This is equal to this expression because we can sum out C from this part of the expression, because on this part is only part that includes C that includes C in the expression. So we have C in all these potentials and factors. So this, if we want to sum out C, it needs a sum product operation. Sum product operation means we need to calculate the product of all the factors and then sum out a variable from the result of the product. In this case, we product all these three factors, frequency tables, and then we will find the frequency of G over this part of the graph. So we calculated the factor for G, which shows we have 4G1 and 8G2 in this part of the distribution. And once we calculated this, we calculate a conditional factor that gives us the frequency of C given G over all the distribution subgraph that we had here. In this case, we have just two, so we don't need more than two variables here. The next step is to eliminate G. So we find all the parts that have G inside them, and then run some product operation over this part. So we will get frequencies of I values in this part of the distribution or graph. Once we eliminated G, we add another conditional factor in our supplementary tree that gives us the frequency of G given I over this part of the distribution. So then we need to eliminate K, and we add another conditional factor here, which gives us the frequency of K given I in this part of in this subtree of the graph. And the final result is the frequency of I, attribute I over the join result. So we can simply generate a uniform sample because we have the frequencies. By the way, if we sum all these frequencies in the marginal of I, it will give us the join size. So we will have the probabilities. If we divide this number with the join size, it will give us the probability of I in the join result. So we can generate a uniform sample of I in the join result. So we use ancestral sampling. By the way, all these calculations are exact, and the factorized distribution that we calculate is an exact distribution. So the sample is an exact uniform of the exact sample. So we use ancestral sampling. We first generate sample for I, and then we generate G for that chosen I, and then C given G and K given I. Once we generated I, then we want to generate G, right? So G becomes, based on Markov properties, G becomes independent from K because I value is observed. So we have the I value. So choosing one G is independent from K. And choosing G is only dependent on the I value we have already chosen. And also it is dependent on the children of the G, all the subgraph that is after G. And since these conditional factors gives us the frequency of G given I in all these subgraphs, so we can simply generate a uniform sample of G given I. So, and then a uniform sample of C given G, and at the end, the sample will be a uniform sample of the join result. Once we found the sample for join attributes, we simply can add non-join attributes as well. But what about cyclic joins? In cyclic joins, this is the graph for query Y from type CH, which is cyclic. In this kind of graphs, we can simply make it acyclic by pulling all some edges or nodes, and then generate a sample for all remaining nodes, and then reject the sample based on that pulled out part of the graph. This is very similar approach to Zhua's approach in this paper, but they need to, there are two differences here. They pull out tables, not nodes or edges. They pull out full tables from the join to make the joins acyclic. But we pull out just some edge or just one attribute from the graph. And also they need, if they have to pull out several tables, they do actual join over those tables, which is not efficient, that we want to avoid it. But if we pull out more than one node from the graph, we do inference on that pulled out graph as well. So during generating samples, we generate the samples for remaining part, and then we reject those samples based on the frequencies in the root of pulled out graph. So these are two differences, and this is the algorithm. These two are the reasons that our approach is much faster than Zhua's approach. For the experiments, we ran experiments on Job, Twitter, TIPCH, TIPCDS benchmarks. You can refer to the paper for all the experiments, but here I will explain just some of them. This plot is for query 16B from Job benchmark. The x-axis is the scaling factor and y-axis is the time in seconds. The green one is for PGMJoins that shows its efficiency is fixed when we scale up the data. We replicate data, and the number of distinct values is fixed in different scaling factors, so the efficiency is fixed. But Zhua's approach is dependent on the table sizes. When we replicate data, the table size increases, but the number of distinct values doesn't increase. So their approach is dependent on the table sizes. In TIPCDS queries, the number of distinct values increases while we increase the scaling factor. Even in that case, we are up to 28 times faster than Zhua's approach. To wrap up, for the first time, we mapped the join random sampling problem to the principal probabilistic graphical models. We introduced an efficient way to generate a uniform sample of the join result up to 28 times faster than SOTA approaches. And also we introduced a new way to deal with cyclic joins. Thank you.